Let us now consider a new class of models, and these are the mass spring damper systems. Now we will go through the following. We'll first look at the models for the individual elements of a mass spring damper system. We'll look at the laws of motion, or Newton's laws of motion. We'll look at or review the idea of free body diagrams. We will also give an overview of the modeling process when dealing with mass spring damper systems. And then we will look at a classic example of that, which is the quarter car model. So in this case, our systems are systems which are made up of mass, spring, and a damper. And these are common systems in mechanical application. A classical example of this is a car suspension, which would have a coil spring, a damper in the form of a shock absorber, which then makes sure that the shock felt by the tire is not immediately translated into a shock on the seat of a passenger, just to make sure that the passenger is comfortable. In fact, if you model the tire itself, you'll find out that it also has the same mass spring damper behavior. So the first element which we will look at is the spring, and the spring looks like this. Normally it's a coiled spring, and when one stretches the spring from the position at rest to a certain position, second position, it tends to resist that displacement. So spring resists displacement, and so the extension of the spring is proportional, or the displacement, in this case that x, is proportional to the force that the spring makes. So which means the more you extend the spring, the more the force, the bigger the force it generates. And the spring has a fundamental constant which we call K, which can be modeled as K, and this K is called the spring's constant. It's characteristic to that particular spring. And ideally, we think of a spring in our case as linear, in terms of that the force is linearly proportional to the extension. So if you have an extension here and a force here, our assumption that there's a linear relationship. Now it has no damping and it's massless. However, this assumption will later know that realistically speaking, this is not true. Another important element is called damper, and it can be shown that the viscous damper resistance to motion is directly proportional to velocity, and the damping constant B in this case is given by in the units newtons seconds per meter, and so the damping force is proportional to the velocity using the damping constant B. Now, what's also important is to take note of Newton's laws of motion. In particular, I want to call your attention to the second law of motion, which effectively implies that the net force acting on a mass is equal to that mass times acceleration. And then the third law of motion, which says the force, reaction is equal to action. So if an object exerts a force Fa on a second object B, then B simultaneously exerts a force Fb on A, and the two forces are equal but opposite in magnitude. So this is important, especially when you have interlinked components on a mass spring dashboard system. So going back in fact to Newton's law of motion, if you look at the initial element, which is the mass in this case, we have just explained that acceleration depends on the net force. In fact, if you have a mass which it's rolling on a frictionless surface. Then according to Newton's laws of motion, mass times acceleration is going to be equal to the net force. And the net force in this case would be equal to F1, which is pulling towards the direction of displacement x, minus F2 minus F3. What's important here to note is the fact that the polarity of F is positive because it's pulling towards the direction of x, but F2 and F1 and F3 in fact are negative because they are pulling in the opposite direction of the displacement x. Now, coming back to just to review what are called free body diagrams. Free body diagrams are a good tool to analyze these mass spring dashboard systems. And one needs to consider as an example here a mass on a spring that's been pulled by a force U0 to give a resulting displacement x. And you need to know that the spring K1 is connected to a stationary, is mounted on a fixed position. So now if we want to get the equation of motion for this mass, we need to draw a free body diagram. Free body diagram is simply a drawing showing the mass and the forces acting upon it. So in this case, at equilibrium, that is when the weight of the force is balanced by the spring. The forces that would be acting beyond that would be as the mass is being pulled by U of t towards the direction, to positive direction x, there would be also another force, which in this case would be the force of the spring. And the convention that we'll adopt in this series of lectures is that because the restorative force of the spring, or the force of the spring, is negative also, we will adopt this convention of writing it this way. In this case, we'll write k times the displacement, but that displacement relative to a certain point. In this case, this point will be 0 because it's relative to a non-moving object here. So the differential equation that we derive will be mass times acceleration is equal to the sum of the forces. The first force is the force, it's U, and then the other force is the force due to the spring, which is K1 times 0 minus Kx. A second illustration here is supposing now here we have the same mass m, which is attached to a spring by another mass mx, and this mass mx moves about the displacement, is displaced, it moves about, its displacement is y1, and then for m the displacement is around y. So if we draw the free body diagram, we will see that we have, in this case, the acceleration, which is, sorry, the force, which is u, and then the other force which pulls back, the spring's force is going to be equal to K1 times y1 minus y. So here the displacement of the spring, which is y, occurs relative to the mass, sorry, to the displacement y1 of the second mass. So the forces in this case are going to be m y dot dot is equal to K1 plus, K1 times y1 minus y plus u. Similarly, for a mass temper system, consider the following diagram where you have a force, you have a mass m being pulled by a force ut, and is attached to a second mass mx by a damper b with damping coefficient b. Now, if you draw the free body diagram of the mass M, there will be two forces. The first would be the pulling force U of t, and then secondly, the force that resists the motion would be the damping force Fb. Now, the damping force would, as initially explained, is proportional to the velocity, and so the damping force B would simply be equal to B times the relative speed. The relative speed therefore means the speed, the velocity divided t relative to y1 in this case, because there's y1. And so the differential equation model for the system, the system that is being mass m, is going to be m double dot is equal to negative the damping force, positive the pulling force, because the pulling force is in the same direction as the displacement y. Now we can therefore say, if we have generally a spring mass system, a spring damper and mass system, the first thing that we need to do when we are modeling such a mechanical system is to identify the elements, the springs, masses, and dampers. And then for each mass, we need to draw a free body diagram. And then in order to derive the ordinary differential equation for that, we will apply Newton's second law of motion. Let's consider then an example of a quarter car model. A quarter car model, as the name suggests, this is a quarter of a car, 1/4. It models the suspension of a car by looking at each wheel separately. So we will look at the impact of the change in displacement, the roughness of the road U on one wheel and tire attached to 1/4 of the body mass M1. So for the quarter car model, we can see that in this case the car is moving on an uneven road, the uneven road being provided by U. The input is U, which is the displacement of the uneven road, and we have two masses, M1 and M2. Now, as suggested by our procedure, we will first take M1, which is mass M1, and then with M1 we'll draw the forces that are acting on mass M1 as a free body diagram. So what we will see is that M1, we have two forces resisting the motion, the damping force as well as the resistive force. And then for M1, therefore, it means that our differential equation is going to be M, the displacement double dot, is equal to negative the spring force and negative the damping force, because both of these forces are acting in the opposite direction of the displacement. Now, by Newton's third law of motion, it therefore means the same forces but in the opposite direction on M2. And so M2 will have the spring force here by K1 and damping force here by C1. And then you will have another spring force due to K2, which is this one. And then you will have another damping force due to C2, which is this one. Now, if we're going to write down the forces, it therefore means that M2 double dot will be equal to the positive spring force, which is Fk1, this one, and then another positive damping force, because they go in the same direction as the displacement, negative that would be the spring force Fk2, and then minus Fc2, which is the damping force. So at the end of this chapter, you should be able to analyze any mass spring damper system please go ahead and consider and revise the relevant sections of the of our reference text as stated in the study guide, and you should be able to attempt some of the tutorial questions dealing with mass damper systems.